Usually when you think about sending a package, right, there is this baseline expectation of logistics.
Yeah, a system.
Exactly. You put something in a sturdy box, you slap a specific address on it, you hand it over to the delivery guy, and you just, expect it to arrive perfectly intact.
Right, because it's a highly engineered, totally linear process. You know exactly where it's going to end up.
But when you step into the world of regenerative medicine, specifically looking at the human body's natural FedEx system, which are exosomes, that predictable delivery route just completely falls apart.
Oh, it's an absolute mess.
It really is. We are looking at a logistical landscape that is, frankly, a nightmare. And that's actually our mission for today's deep dive for you guys. We're exploring the massive promise of exosomes and, more importantly, the incredible kind of crazy engineering hacks scientists are forced to use to actually make them work.
Yeah, and if you are already following the latest in cellular biology, you likely know the foundational basics here, right? They are these microscopic membrane-bound vesicles, like 30 to 150 nanometers wide.
Tiny. Just incredibly small.
Super tiny, and basically every single cell in your body secretes them. They carry this really specific payload of proteins, lipids, and nucleic acids.
It's like how they text each other.
Exactly. It's the primary way cells communicate, coordinate immune responses, and trigger complex tissue repair.
And the clinical promise here feels just limitless. I mean, we're talking about utilizing these microscopic messengers to cure autoimmune diseases or regenerate torn muscles or even fix the gut lining.
The potential is massive.
It is. But as I was digging through the stack of scientific sources for this deep dive, the exact same glaring problem just kept surfacing. It seems like the human body actively wants to intercept these packages and literally throw them in the trash.
Yeah, and confronting that biological reality is really step one for any of these therapies, because if you take a syringe full of highly concentrated therapeutic exosomes and simply inject them systemically,
Like into a vein or something.
right, into a vein or the peritoneal cavity or even subcutaneously, the body's natural defense and filtration mechanisms just go into absolute overdrive. The vast majority of those systemically injected exosomes are rapidly recognized and just consumed by macrophages in the reticuloendothelial system.
Okay, wait, pause right there. The reticuloendothelial system. Break that down for me, because that sounds like, heavy textbook jargon. What is that system actually doing?
Fair enough. Think of it as the body's internal security and sanitation department.
Okay.
It's this vast network of cells, primarily those macrophages we just mentioned, and they're located heavily in your filtration organs. So the liver, the spleen, the lungs, and the gastrointestinal tract.
So they're the bouncers.
Exactly. Their entire biological imperative is to constantly scan the blood and lymph for foreign particles, dead cells, or debris, and just clear them out immediately.
So to these vigilant macrophages, a sudden massive flood of injected exosomes looks exactly like foreign debris that needs to be swept up to protect the host.
Spot on, and the timeline on that sweep is staggeringly fast, too.
How fast are we talking?
Well, the research notes that as early as 2 hours after injection, these carefully cultured, incredibly expensive exosomes are just gone from the blood circulation.
2 hours. Wow.
Yeah, they end up trapped and accumulating in the liver and spleen, completely missing the torn muscle or damaged organ you are actually trying to treat.
Which has to create a profoundly frustrating scenario for clinicians,
Yeah.
right? You're trying to deliver this highly specific regenerative signal to damaged tissue, but your delivery vehicles are being intercepted and dismantled by the body's own trash collectors before they even get close.
It's incredibly frustrating.
It feels like throwing a million letters out of an airplane, aiming for one specific mailbox in a tiny town, and just hoping the wind carries one of them there.
That's a great analogy.
Because the reality is 99% of those letters are just going to end up lost in the ocean.
Yeah.
And in this case, the ocean is the liver and the spleen.
Precisely. And that intense clearance problem, it applies to localized topical delivery as well. You might logically assume the fix is just, hey, apply them directly to the target.
Right, like if you have a severe skin issue or a scratch on your eye, just drop the exosomes right there on the surface.
But you can't. The human skin is guarded by these tight epithelial junctions. It acts as a physical brick wall, blocking these nanoscale vesicles from penetrating into the deeper tissue layers.
And even if they could somehow breach that wall, you have the issue of rapid fluid turnover, right?
Oh, yeah.
Like on the surface of the eye or the skin, sweat and tears are constantly flowing. So the therapeutic exosomes are literally washed away before the target cells even have the time to take them in.
Exactly. And the compounding effect of this clearance rate creates an astronomical manufacturing bottleneck for the pharmaceutical industry. Let's look at the raw numbers from the literature here.
Yeah, lay it out for us.
The typical yield of a standard exosome isolation process is minuscule. Laboratories are often harvesting less than 1 microgram of exosomal protein from 1 full milliliter of cell culture medium.
Okay, so 1 microgram per milliliter. But what's the actual dose you need?
Well, the sources mention an effective therapeutic dose just for treating a single mouse is in the range of 10 to 100 micrograms.
Wait, so you would need up to 100 milliliters of culture medium just to treat one tiny mouse?
Yes. So extrapolating that to a human patient, it reveals the sheer impossibility of the situation.
Mm.
To compensate for the liver and spleen intercepting almost all of your payload, you would have to administer an overwhelmingly massive dose.
The financial cost of that alone.
Exactly. The cost and the sheer physical logistics of producing human-scale doses at high purity would bankrupt any lab. We just cannot produce enough exosomes to simply outpace the body's natural clearance systems using traditional free-floating injection methods.
Which means we can't flood the system. We have to outsmart it. We have to physically pin the package down so the body can't wash it away. And this is where the bioengineering strategies get truly fascinating, starting with hydrogels.
Yeah, hydrogels provide a brilliant mechanical solution to what is inherently a biological problem.
Right.
These are highly porous, biodegradable polymer networks that can absorb massive amounts of water without dissolving. So scientists are taking these advanced hydrogels and embedding the therapeutic exosomes directly into the three-dimensional matrix of the gel.
So instead of a free-floating liquid injection that immediately gets swept into the bloodstream by the macrophages, you're creating a localized physical trap.
A trap that you place directly at the site of the injury. Imagine you have a surgically repaired torn rotator cuff. The surgeon places this exosome-loaded hydrogel directly onto the repaired tendon.
Oh, that makes sense.
Right, the hydrogel physically holds the exosomes in place. The circulating macrophages can't easily sweep them away, and the local fluid turnover can't wash them out of the joint.
Because it's porous and biodegradable, so it kind of acts like an automated slow drip system. As the gel slowly breaks down over days or weeks, it drips out a highly localized, concentrated dose of exosomes exactly where the healing tissue needs it.
Exactly.
So the letters aren't being thrown from an airplane anymore. You basically superglued the mailbag to the recipient's front door.
That's exactly it. And that sustained localized presence is the critical factor. It gives the target cells the necessary time to internalize the exosomes via endocytosis and actually read those complex regenerative signals. But hydrogels are just one method of physical manipulation. Scientists are also using energy, specifically mechanical sound waves, to hack both the production and the delivery of exosomes.
Now, the ultrasound application is where things get genuinely counterintuitive for me. We've established that these lipid vesicles are microscopic, fragile bubbles. But researchers are blasting them with mechanical shear stress using this technique called low-intensity pulsed ultrasound, or low-IPUS.
Right. Lamina is primarily being utilized to stimulate the parent cells, so the actual living cells that manufacture the exosomes in the lab. The ultrasonic waves generate intense mechanical shear stress across the cell membrane. This causes a sudden increase in surface tensile strength and temporary membrane contraction.
Okay, wait, I need to understand the underlying mechanism there. Why does physically vibrating a cell make it produce more exosomes? How does the cell physically interpret that vibration?
Okay, so the mechanical vibration mimics the severe physical trauma of a bodily injury. The cell feels that sheer stress and is biologically tricked into thinking the surrounding tissue is under physical attack.
Oh, wow.
Right? It triggers the cell's emergency first aid response. The parent cell assumes its neighbors are damaged and urgently need help, so it drastically ramps up its communication efforts to coordinate a repair protocol. Applying labias to Schwann cells, for example, tricks them into increasing their exosome productivity by threefold.
Threefold.
Yeah, and the concentration of those exosomes increases by 5.7-fold compared to static, non-vibrated cultures.
So you're basically putting the exosome factory on a vibrating treadmill to simulate a crisis, forcing it to pump out more product.
Exactly.
That logic tracks for the parent cell, but the sources also mention another technique, which is sonication. And they're using sonication directly on the isolated exosomes themselves to force external drugs into them. Now, if an exosome is a delicate little 100 nanometer soap bubble of lipids, wouldn't blasting it with sonication just completely obliterate the package?
It absolutely seems like it should destroy them, but this speaks to the unique, highly dynamic thermodynamic properties of lipid bilayers. Sonication does produce intense mechanical shear forces that violently disrupt the membrane, but it doesn't permanently destroy it.
So what does it do?
Think of the exosome less like a fragile soap bubble that pops and vanishes forever, and more like a microscopic, self-healing sponge made entirely of fats. When you apply sonication in the presence of a drug, and the sources look at an anti-inflammatory compound called berberine, the ultrasonic energy temporarily tears open tiny pores in that lipid membrane.
Allowing the external drug to just rush into the vesicle through those temporary microscopic tears.
Yes. The physical agitation essentially drives the berberine straight into the hollow core of the exosome. And the moment the sonication machine is turned off, the thermodynamic properties of the lipid bilayer cause it to naturally and rapidly self-assemble.
It just heals itself.
Almost instantly, it seals those pores back up, permanently trapping the drug inside. This specific method achieved a 17.13% loading efficiency for berberine, creating a supercharged exosome that provided a sustained release over 48 hours to severely alleviate inflammation and spinal cord injuries.
Mechanically forcing extra cargo into the mail truck right before it departs. I love the ingenuity of that. And we're already seeing this kind of ultrasound hack move into real-world clinical applications, particularly in dermatology and aesthetics. The Chimera Lab study we reviewed is a perfect example of this.
Oh, for sure.
They were trying to enhance tissue biostimulation in the face and neck, and they didn't just rub an exosome cream on the skin and hope for the best.
No, they engineered a highly orchestrated sequence of chemical and mechanical steps to forcefully overcome that tight epithelial barrier we discussed earlier. They started with a glycolic acid wash, immediately followed by a sea salt exfoliation.
Creating what they refer to as a homing inflammatory environment.
Right.
They're basically ringing the alarm bells in the skin, causing a mild controlled damage so the cells are actively looking for repair signals. Then they applied a nitric oxide serum to act as a potent vasodilator, opening up the microvascular pathways.
And then the critical final step involves applying a topical emulsion packed with millions of exosomes, hyaluronic acid, and dilute calcium hydroxyapatite. To breach the epithelial brick wall, they used a 3 megahertz cavitating ultrasound device directly on the surface of the skin.
Using sound waves to physically push the package through the mail slot.
Exactly. The cavitating ultrasound drives the exosome emulsion significantly deeper into the facial tissue than it could ever possibly penetrate on its own.
It beautifully illustrates that overcoming clearance issues requires treating exosomes not just as biological entities, but as physical nanoparticles that respond predictably to mechanical forces.
No.
But localized hydrogels and ultrasound devices, those are strictly for external or surgically accessible areas.
Right. Which brings us to the ultimate internal nightmare.
Yeah. What if the target is deep inside the body, in an area constantly churning with fluid, harsh enzymes, and acid? I'm talking about the human gut.
Yeah, that's a tough one.
If you want to treat conditions like inflammatory bowel disease or IBD, how do we bypass the IV needle entirely and deliver exosomes orally? Because if you just swallow these fragile lipid bilayers, the highly corrosive stomach acid is going to rip them to shreds in a matter of minutes.
Oh, absolutely. Surviving the corrosive acid bath of the digestive tract is widely considered the holy grail of exosome delivery. To solve this monumental challenge, researchers engineered an incredibly innovative microcapsule called CSE that stands for chitosan sodium alginate. They use this complex polymer shell to encapsulate exosomes derived from endometrial regenerative cells, known in the literature as ERC exos.
Chitosan and sodium alginate. Let's unpack the chemistry there. They essentially built an armored transport vehicle for the exosomes, but how does it actually know when to open its doors?
So the chitosan alginate matrix is specifically synthesized to remain tightly cross-linked and stable in highly acidic environments. When you swallow this microcapsule, the matrix holds strong. It completely protects the delicate exosomes from the simulated gastric fluid in the stomach.
So the harsh digestive enzymes and low pH just bounce right off the armor.
Exactly. But the chemistry of the capsule is engineered to be highly sensitive to surrounding pH changes.
So once it leaves the acidic environment of the stomach and enters the distinctly alkaline environment of the colon, that chemical change in pH acts as a trigger mechanism.
You got it. The sudden shift to an alkaline environment rapidly disrupts the cross-linking of the polymers. The hydrogel matrix begins to safely dissolve, releasing the perfectly intact payload of exosomes exactly where the IBD inflammation and tissue damage is actually occurring.
It unlocks the payload right at the destination.
Yeah.
But the precision goes even deeper than that, right? It's not just indiscriminately dropping packages in the colon and hoping they get picked up. There's a biological lock and key mechanism that takes over the moment the capsule dissolves.
Yeah, the inherent biology of the exosome perfectly complements the synthetic engineering of the capsule. Once the ERC exosomes are released into the colon, they aren't just floating blindly. These specific exosomes natively carry a protein on their surface called MFGE8, milk fat globule EGF factor 8.
And what does that specific protein actually do in the gut?
It acts as a highly specific VIP access pass. MFGE8 naturally binds to integrin receptors that are densely located on the surface of the intestinal epithelial cells.
Oh, wow.
Yeah, and this tight binding greatly enhances the cellular uptake of the exosomes. Once internalized by the damaged cells, the exosome cargo triggers a very specific biological cascade called the PI3-AKT-mTOR signaling pathway.
Okay, you have to break that alphabet soup down for me. The PI3K pathway, what does that actually physically do to the patient's gut?
Sure. Think of the PI3-AKT-mTOR pathway as a master biological control switch for self-survival and growth. In a patient suffering from IBD, the intestinal cells are heavily damaged and actively undergoing apoptosis, which is programmed cell death.
So the intestinal barrier is literally breaking down, causing massive painful inflammation.
Exactly. But when the exosome cargo triggers this specific pathway, it physically flips the switch. It instructs those dying intestinal cells to stop undergoing apoptosis, start rapidly proliferating, and aggressively rebuild those tight junctions. It forces the intestinal barrier to repair itself from the inside out.
That is incredible. And if you look at the spatial difference in this delivery route, the advantage is massive. If you were to administer exosomes systemically via an IV for IDD, those vesicles would have to navigate the entire circulatory system, survive the macrophages in the liver and spleen, and just hope a tiny fraction makes it to the gut microvasculature.
Exactly. But with the oral capsule, you are delivering the exosomes directly into the gastrointestinal lumen. This allows the intestinal epithelial cells and the local macrophages to act as the absolute first responders. They take up the exosomes immediately, completely bypassing the filtration organs that cause that manufacturing bottleneck.
We aren't dropping letters from planes anymore. We put the package on an armored train that drives straight to the destination and automatically unlocks the door. It's a monumental leap forward. But, a delivery system is only as good as the package inside. How do we know these exosomes are actually carrying the optimal instructions to heal the gut or a torn muscle?
That question right there represents the most crucial frontier in regenerative medicine right now. Scientists have realized they do not have to passively accept whatever exosomes a cell happens to be making naturally.
That can change them.
Oh, yeah. They can actively train or pre-program the parent cell to print superior therapeutic messages before the package is ever mailed out.
Because the exosome is ultimately a biological snapshot of the cell it came from, right?
Yeah.
The cargo, like the specific microRNAs and proteins it carries inside, directly reflects the physiological state and the lived environment of that parent cell.
Exactly. So if you intentionally alter the environment the parent cell lives in, you fundamentally alter the resulting exosomes it secretes. The source has highlighted a fascinating method for this called hypoxic preconditioning.
Hypoxic meaning low oxygen.
Right. Researchers took hair follicle mesenchymal stem cells and deliberately starved them of oxygen in an incubator.
Which is wild. You'd logically think suffocating a cell would just severely damage it and result in weaker, compromised exosomes.
It seems highly counterproductive, but it actually induces a state of extreme yet controlled cellular stress. The cells panic, but in a highly productive way.
How so?
The parent cell assumes the surrounding tissue is actively dying from a severe lack of oxygen, so it urgently changes its manufacturing process. It starts pumping out exosomes that are densely packed with a specific microRNA called miR-214-3P.
And what does that specific microRNA actually do for the patient?
It acts as a potent set of emergency repair instructions. When these stress-tested exosomes are applied to a colitis model, the miR-214-3P aggressively promotes mitochondrial autophagy, meaning it cleans out damaged cellular components, and it severely limits oxidative damage in the gut lining.
So by starving the parent cell, you turn it into a dedicated hyperactive factory for survival signals. We're actively hijacking the cell's emergency broadcast system for targeted therapy.
It makes perfect sense when you think about it. The cell prepares for the worst, and we harvest that intense preparation.
But if starvation isn't precise enough, the sources show we can bypass environmental stress and just rewrite the instructions at the DNA level. Researchers are genetically engineering the parent cells to dictate the exact cargo.
Yes. The genetic manipulation offers unprecedented granular control. If researchers knock down a specific gene in a stem cell, like the TSG6 gene, the exosomes it produces completely lose their healing power. They essentially become empty blanks, proving that specific genes strictly dictate the therapeutic value.
But if you go the other direction, if you overexpress certain genes, like NLRP3, the results are staggering. The parent cell is forced to pack the exosomes full of highly potent anti-inflammatory cytokines, specifically IL-10.
Right, and IL-10 is a powerful protein that drastically reduces inflammation and rapidly suppresses immune overreactions. By overexpressing the NLRP3 gene, you are literally dictating the exact molecular contents of the male. It represents a total paradigm shift.
We're moving from simply harvesting naturally occurring vesicles to engineering custom precision-guided biological drones. You control the parent cell's genetics to dictate the cargo. You use sonication to forcefully load additional drugs into the lipid sponge, and you use pH-sensitive microcapsules or porous hydrogels to ensure the drone reaches its exact target without being intercepted by the immune system's trash collectors. The chain of problem-solving across these disciplines is unbelievable.
It truly is a testament to the immense cross-disciplinary ingenuity required to make regenerative medicine a tangible, scalable reality.
It absolutely is. And before we wrap up today, I want to leave you, the listener, with a final, slightly mind-bending thought to ponder based on the research we've unpacked. We know that exosomes aren't just a human phenomenon.
Right, plants make them too.
Exactly. Edible plants, things like ginger, grapes, and tea leaves, produce their own version of these called plant-derived exosome-like nanoparticles, or PDENs.
And beautifully, because they come from food we've evolved over millennia to eat, these plant vesicles are naturally designed to survive the harsh, acidic environment of the mammalian gut.
So they're naturally orally bioavailable. Combine that natural evolutionary resilience with the genetic engineering and pre-programming techniques we just discussed. Could the future of medicine bypass sterile laboratories and expensive IV injections entirely?
That's the dream.
Right. Imagine a world where treating a chronic autoimmune flare-up or a severe inflammatory disease doesn't mean sitting in a clinic for an infusion. Imagine simply eating an apple that has been specifically engineered on a cellular level to produce plant exosomes containing custom, nanoscale biological instructions.
Delivered straight to your immune system as you digest your lunch.
Exactly.
It completely redefines the concept of food as medicine.
It really does.
Yeah.
It turns out, to get the mail delivered properly, sometimes you don't need a stronger box or a faster plane. Sometimes you just need to grow a better apple. Thank you for joining us on this deep dive into the microscopic world of exosome delivery. We'll catch you on the next one.